This is lecture 5 from chapter 12, picking up with talking about alcohols. So we're going to talk a little bit about glycerol. So we saw in the last lecture that glycerols, these are alcohols where there are 3 hydroxyl groups that have replaced the hydrogens. And glycerols, especially the reason why I want to talk about these guys, so we saw in the last lecture glycerols or glycerin. These can be used in products like toothpaste and lotions, but if we take glycerol and react them with something like nitric acid in the presence of sulfuric acid, we get a compound called glycerol trinitrate. And you might go, I don't know, what is that? Aha! It has a common name, and I bet you recognize that one. So the common name for glycerol trinitrate is nitroglycerin. And I will post the link to this video after this lecture in PantherLearn so you can see what nitroglycerin is as far as what it takes to make it, but also how it reacts because just reacting the glycerol with nitric acid and in the presence of that sulfuric acid, creating that glycerol trinitrate, takes that glycerol, that glycerin that is a pretty benign material and turns it into a fairly reactive one. It is a clear oil, as you'll see in that video, that is violently explosive and unstable. It doesn't take much of a hit in order to get it to ignite. So it's a very interesting compound in that sense. What was interesting even more so was that this gentleman, Alfred Nobel, again, you might recognize that name, discovered taking it and mixing it with siliceous earth, basically silica-based earth, made it more stable but still explosive. So he then took that material and called it dynamite. Packed it into tubes for easy use. It would stay stable. You could carry it around in your backpack or whatever it might be, put a fuse in it and still use it for explosions, but it wouldn't explode just, being jostled around in your pack or whatever. This is actually how Alfred Nobel made a lot of his money. And the money that he made, he was actually quite guilty about having created this very destructive material, and so he took that money and created the Nobel Prizes that you are familiar with today. So they were originally funded by the money that Alfred Nobel made off of creating dynamite. All right, that's the end of the alcohols. The next group are the organic acids. So this is the next functional group. And you can see that this guy is going to be connected to a hydrocarbon. Now, this has got a little bit different structure to it. So you can see that the structure is a carbon, oxygen, oxygen, hydrogen. So you've got the hydrocarbon, but you have the carbon bonded to the oxygen in one direction and then the hydroxyl, the OH, in the other direction. So that's an important difference. There's a double oxygen bond and then an OH. You need this whole structure to make the organic acid. So these organic acids are chemically called carboxylic acids because of this COOH functional group or a carboxyl group. And so again, that structure, you can see it's drawn down here. This is the simplest organic acid. So you can see it. This is the hydrocarbon, and it would have been methane originally because it would have had the hydrogens going in each direction, but we've now replaced it with a double bond to that oxygen. That's the one clue, you're looking at an organic acid. So you've got a double bonded oxygen, and if you've got a hydroxyl group, that gives you the COOH. So the simplest organic acid was actually originally distilled from ants. That's why we've got the little ant up here in the corner. This is called formic acid. And it's not just found in ants, it turns out. That's where originally it was distilled from, but we actually find formic acid in the stingers of ants, bees, and plants. So if you've ever been stung by a bee or stung by an ant, or I believe the other one are stinging nettles, they all contain this formic acid, and so this is what makes it burn. It's actually an acid, so it's actually burning you. So there are other organic acids that you are familiar with. So you've got acetic acid. This is going to be created when ethanol oxidizes, so when ethanol is exposed to oxygen. So this is why the acid in vinegar, this is the acid in vinegar, so that smell that you're familiar with, this is acetic acid that creates that smell, and that acidic, that kind of tart taste. But this is also why wine can go sour. So I don't know if any of you are familiar with this, but wine can go bad. And what happens is that the products in the wine actually is going to create acetic acid. So ethanol is going to oxidize, and it's going to form this acetic acid. It's going to get some of those hydrogens replaced with the structure that we saw with adding in oxygens. And so this is what can make wine sort of taste sour or like vinegar over time. Another acid that you know that's an organic acid is citric acid, and I bet you can probably name some fruits off that citric acids are found in. Lactic acid, this is found in sour milk, not probably your favorite way to find it, but also buttermilk, sauerkraut, and pickles contain lactic acid. So that's what creates that kind of, again, that I want to say the mouth clenching, pinching kind of flavor in something like sauerkraut and pickles. A lot of organic acids today are used as raw materials for making things like fabrics, film, paints, and so forth. And they're an integral part of the process of those types of materials. There is one more, I have to keep moving myself around, sorry. There is one more organic acid that I want to just point out, because this is actually a pretty important one, insofar as I'm sure many of you have actually used it. So salicylic acid is an organic acid that's found in the bark of willow trees. So you've probably seen one of these before. Willow trees are actually found here in the northern part of the United States. And this is salicylic acid up here. The carboxyl group that makes it an organic acid is right here. So there's where the carbon would be. Or I'm sorry, this is the hydrocarbon. The carbon is actually right here, bonded doubly to the oxygen, and then you've got oxygen and hydrogen out here. So these diagrams don't have all the carbons drawn into them, just so that you don't have to have carbons drawn all over the place. But if you have these lines between like this, this means that there are 2 carbons on either end of the line. So what people used to do is they used to take the bark from these willow trees and brew them, brew that bark in hot water and drink it, and it would reduce fevers and work as a painkiller. So there was a side effect, and there are some people who still use it today. The problem is this other side. I'm not going to talk about phenolic groups, but this group causes problems because it actually creates an acidic system. So this actually causes nausea and upset stomach in some people, which, depending on the fever and the pain that you're experiencing, that might not be such a bad side effect. But Bayer, the company Bayer, took this group and modified it into a different group, this ester group, which we won't talk much about either. But the ester group actually won't create an acidic environment, but gives you still the effect of the salicylic acid. And by modifying it, created, acid or aspirin. And so, like I said, many of you have probably taken a version of salicylic acid because Bayer originally modified the salicylic acid and turned it into aspirin. So if you've ever taken aspirin, you've taken a modified version of this organic acid. All right, esters. So this is an ester group. It looks a little bit like an organic acid. So if you look at the structure, we've got hydrocarbon over here, hydrocarbon over here. We've got carbon bonded to oxygens, one with a double bond, one with a single bond. And what's the deal with esters? Like I said, they're similar to organic acids, except that hydrogen that would be attached to the oxygen is been replaced by a hydrocarbon. The thing with the esters that you would be most familiar with is that these have fragrances. And the different items that are up here on the picture are actually esters that you are familiar with. These are what give fruits and flowers their odor and taste. So they're pretty important. They obviously are found naturally, but we can synthesize a lot of these. Actually all of the ones that are up here, pineapple, orange, banana, peach, and rum, we have natural ones obviously from the natural products, but we also have been able to synthesize all of them. So we've been able to synthesize the ester that gives the smell and taste of these different fruits. In the case of these guys over here, the bananas and oranges and pineapples, or the taste of the product of the rum. Now the synthesized ones might not be exactly the same because the taste is not just the esters but other chemicals as well, but it gets pretty close because most of the taste and odor is coming from the esters. The last group of functional groups that I want to talk about are the amines. So the amines, these are where you have a hydrocarbon that has a nitrogen with two hydrogens bound to it. So you can see here's our hydrocarbon, we've got a nitrogen, two hydrogens bound to it. So why do I want to talk about these? Well, these are actually best known in amino acids. This is actually a big building block in organisms like ourselves. So we actually use a lot of amino acids in one of the polymers that we'll talk about later in this chapter. The other one that I just want to show are some of the low mass amines. They're known for their offensive odors. You might notice the names down here because these are the two main low mass amines, putrescine and cadaverine. The names do describe their odor. These two amines are commonly found with dead bodies and are actually a big part of the odor that comes from decomposing bodies like animals and so forth. So this is part of what creates that smell, as well as the bacteria breaking down tissue. So this is the end of the section on functional groups, and we'll pick up with the next section in our next lecture.